We only know of one place in the entire universe that has life, and that is right here on Earth. So when we search for other life out there in the universe, we tend to search for what we know. We look for water and methane and a whole bunch of carbon-containing molecules because we know that that's the recipe to get life here on Earth. But what if life out there in the universe is not life as we know it? And perhaps we're missing the signs that it's there because it doesn't have the same signatures of Earth life. Now this is a real possibility, and there are a bunch of astrobiologists and astrochemists who are working through all the different possibilities, all the different options for what life could look like if it didn't look like life here on Earth. So I figured, let's do the same in this video. Now there are a whole host of differences we could talk about, and I'm not going to touch on the differences of like where life gets its energy source from. So for example, from photosynthesis versus energy from like hydrothermal vents, or any environmental differences where like life has adapted to like stronger or weaker gravity. I'm just going to purely focus on like the fundamental biochemistry and how that could be different from life here on Earth. So let's dive in, and first we're going to chat about solvents. So if it's not water like on Earth, what could life use instead? Then we're going to talk about organics. So if it's not carbon-based life like here on Earth, what could it be instead? Then chat about chirality. So could life be a mirror image to here on Earth? And then finally we'll chat about how we'd even find life as we don't know it. And if you love deep dives like this into topics on the cutting edge of science, then why don't you check out Nautilus magazine, who are the sponsor of this week's video. Nautilus is my favorite science magazine because it explores the big ideas in science. You know, the ones that will still be debated long into the future. Now, Nautilus stories extend across all disciplines in science, but I know that you are all gonna love its Cosmos section, which also explores ideas in astrobiology and the search for life in the universe. Now, along with their incredible science reporting, Nautilus is also bursting with original artwork and illustrations, which have made Nautilus a winner of the ASME Best Style and Design Award. It's this merger of like science, art, and culture that makes Nautilus stand out, and it's why I absolutely love it. You can join as a digital-only member or in print, and you'll get 6 beautifully illustrated, award-winning collectible editions per year that look wonderful on the coffee table. So join me in reading Nautilus by heading to joinnautilus.com/Dr. Becky, and you'll get 15% off your membership. So a big thanks to Nautilus for sponsoring this video, and now let's dive into all of the details in terms of the different biochemistries that could exist out there in the universe. And let's start first with solvents. And if it's not water like on Earth, what solvent could life use instead? So first of all, we better define what actually is a solvent. Well, it's fairly simple. It's something that you can dissolve other things in. So for example, yes, water is a solvent because you can dissolve something like salt, which in chemistry terms is your solute that you are dissolving in your solvent, your water, to get your solution, which is then your salt water. And solvents are really useful because what happens is you can essentially take 2 different substances, like 2 different molecules that would never normally react if you just went and mix them together, but dissolving them both in a solvent could actually make them react and allow a chemical reaction to take place. The solvent essentially gives you a pathway to the chemical reaction. And this is why solvents are so important for life, because essentially it gives a pathway for the biochemical reactions that you need to take place, whether that actually is like the construction of proteins from amino acids or the construction of DNA, or like as an active participant in the chemistry because it's actually needed by life to survive. Now, there are a lot of substances that fit the description of solvent that, you know, you can dissolve something else in it. But to be a good solvent for life, there are a couple other different criteria that you need. You need to be able to dissolve some molecules, like the ones that are actually needed in biochemistry, but not others that would be harmful to life. Then you also need it to play that active role in the chemistry. It can't just be passive, allowing chemical reactions to take place within it, but not actually like taking part in the chemical reactions as well. But then there's also a load of different environmental constraints on solvents as well. So you need a solvent to be both stable and in liquid form on a planet's surface. So that's very temperature and pressure dependent, right? Because, you know, for it to not just be a liquid rather than a solid or a gas at a planet's surface, you also need it to to be specifically like the right viscosity, like the right sort of flowability in terms of the liquid as well, because if it's too gooey, then you're not going to be able to actually perform the function of a solvent in allowing those chemical reactions to take place within it. Plus, it needs to be readily available, right? It's no good if wild temperature swings mean that the solvent evaporates and the environment isn't replenished with it again. So you need some sort of cycle of the solvent as well, so that you always have this new source of it, like the water cycle here on Earth. So yes, water ticks all of those boxes here on Earth. But what about other solvents that you might have come across in a chemistry lab during your school days? What about those solvents? Can they be useful solvents for life? Well, ammonia is often a really common one that people come across, but unfortunately ammonia is just not long-lived enough. It's not stable enough on a planetary surface to be a good solvent for life. Neither is like sulfur dioxide or hydrogen sulphide or hydrogen fluoride either. But there are sort of three front runners that people consider when it comes to good solvents for life. There's liquid carbon dioxide, liquid sulphur, and liquid sulphuric acid. Let's start with liquid carbon dioxide, CO2, which, as we know, here on Earth is a gas, at least at Earth's surface temperature and pressure. But at colder temperatures and at much greater pressures than you have in the atmosphere on Earth, carbon dioxide is a liquid. So you could have liquid carbon dioxide on a planet that was quite cold and also had a very dense atmosphere, kind of like a cold Venus. And perhaps you could get that around a red dwarf star, which is a lot smaller and cooler than the sun, so it gives off a lot less light to warm the planets around it. So that's promising, along with the fact that carbon dioxide is also produced by volcanoes. And volcanic activity is really common across the solar system, not just on Earth. So if it's pretty common in the solar system, it's likely it's pretty common in other star systems out there in the universe, which means then you have a source that can constantly replenish the carbon dioxide through, not like a water rain cycle, but like a volcanic cycle. In terms of like, is it a good solvent for life? Well, it's pretty good at that whole, dissolving some molecules, but not others. And also, it's a great source of carbon for any carbon-based life forms. More on that in a little bit. But it's a very unreactive solvent. So it allows like chemical reactions to take place through it, but doesn't actually take an active role in those chemical reactions. So what about liquid sulfur instead? Which is incredibly rare here on Earth, but again, we know that it's produced by volcanoes. So some objects could have a bumper supply of it, like Io, Jupiter's moon, in our own solar system. But there's a very narrow temperature range between like 120 to 160 degrees Celsius, where not only is it a liquid, but it's a liquid of the right viscosity. Otherwise, it essentially ends up kind of like the consistency of toothpaste. We know that it is very reactive and it does take like an active role in the, chemical reactions that take place within it. It's much better at doing that than water, for example. But it's more of our own lack of knowledge that scuppers us here. We don't really know like which molecules are actually soluble in liquid water or not, and whether it has that sort of like selective solubility that we were talking about. So what about liquid sulphuric acid instead? Well, again, it's a very common volcanic gas, and it is liquid at the temperature and pressure ranges we typically find on Earth, but also up to higher pressures as well, like what's found in the clouds on Venus, which are far drier and far more acidic than any place we have on Earth. Plus, we know that sulphuric acid is a great solvent. It's stable, it's long-lived, it dissolves some molecules but not others, and it takes an active role in the chemical reactions between the solutes that are dissolved within it. In fact, of all three of the solvents that we've talked about, sulphuric acid ticks the most boxes. Which is weird, right? Because you hear sulphuric acid and you think like dangerous, corrosive acid, which turns into just one big carbonized blob in less than a minute after it's exposed to sugar. Another key molecule for supporting life. But it's been shown that the complex organic molecules that you need for life are capable of forming in sulphuric acid, just in a completely different way than they do in water as the solvent on Earth. Plus, the building blocks for DNA are stable in sulphuric acid, although DNA itself isn't stable. The bonds between those building blocks break apart really easily. So you would need another like genetic molecule that was stable in sulphuric acid if it was going to be a solvent for life. And recently, Petkowski and collaborators have suggested that molecule could be what's known as PNA, so peptide nucleic acid, rather than DNA, which stands for deoxyribonucleic acid. Plus, Duzdevich and collaborators have also recently shown that molecules build large structures like membranes and tubes in sulphuric acid as a solvent, and that could be the precursor to the building of things like cells. So that's why of these three solvents that we've chatted about, sulphuric acid is considered the front runner, and it's why there's renewed interest in sending, space missions back to Venus, specifically to study the atmosphere of Venus, which has really high concentrations of sulphuric acid. For example, the Da Vinci mission to Venus, although that is now in danger of being cancelled thanks to the proposed NASA budget cuts. More on that in last week's Night Sky News video. If you want to check that out, I'll link it below. Or you've also got the proposed Morning Star mission to Venus, which is both privately and publicly funded. It's purely astrobiology focused, this mission, which is not always the case. Usually it's like astrophysics focused, with astrobiology as like a little side shoot. But here the science goal is specifically to search for complex organic molecules in all of these sulphuric acid cloud droplets in the atmosphere of Venus, with the hope of, maybe even pointing towards life, and maybe explaining that detection of phosphine in Venus's atmosphere from a few years ago. A molecule that's only produced by life here on Earth, but we know the conditions in Venus' atmosphere are vastly different to here on Earth, so it could also be that there's just some unknown chemistry, unknown to us anyway, that's happening in the atmosphere of Venus, because there is still so much that we do not know. That list of the three frontrunners is nowhere near complete. There could easily be another solvent that we haven't even thought to consider yet that could be a great solvent for life as well. But it's not just the solvents that could be different. It could also be the building blocks that actually make up the molecules responsible for all this biochemistry as well. Which brings me to part 2, the organics. If it's not carbon-based life like here on Earth, what could it be instead? Now this might be an idea that you've come across when reading or watching sci-fi before. Instead of carbon-based life, it might be silicon-based life. So where does this idea come from? Well, carbon is crucial for life on Earth. Well, every atom of carbon can create up to 4 really strong bonds with other atoms. That allows the formation of really stable, really long, complex molecules like proteins, amino acids, and DNA that form the structure of life here on Earth and power it too. But that doesn't mean that there aren't other atoms that are capable of creating these really strong bonds and all of these chain-like molecules. The reason carbon can do this is because it has 4 electrons in its outer orbit around the atom. But this outer orbit is actually capable of holding 8 electrons, which means each of these 4 electrons can bond with another electron from another atom and then create these chains with carbon at the very center, making everything super stable. Now, carbon is the lightest atom that has these 4 electrons in its outer orbit. But if you flick through the periodic table to ever heavier atoms, the next atom that you get to with 4 electrons on the outside is silicon. In fact, the periodic table is arranged so that each column of elements has the same number of outer electrons. So yes, you've got carbon and silicon, but also technically germanium and tin and lead, etc. The problem is the lighter elements are much more common in the universe than the heavier elements. So hydrogen and helium are the simplest atoms and most common. But for anything heavier, you then need nuclear fusion in stars, or even at the end of a star's life in a supernova, to actually make those heavy elements. Plus, you can only make the elements up to iron through nuclear fusion. Beyond that, you need something like a red giant star and a reverse radioactivity process where lighter atoms actually capture neutrons to make heavier elements. So if you're looking for an atom that's able to make these really strong bonds with other atoms, so that you can make these really long chain molecules that are really stable so that you can encode biological information, and it needs to be common enough in the universe that you find it in a great enough abundance on a planet so that life can thrive, then carbon is your best bet. But if not carbon, then silicon is the one that gets the most attention because it's the next heaviest. Because like carbon, it can create multiple bonds with other atoms that allow the creation of these long chain-like molecules. But the bonds that silicon makes with other atoms are much weaker than the ones that carbon makes with other atoms. Just because the electrons in silicon are further out from the center, the nucleus of the atom, so they're just more weakly held. Plus, although silicon is still a relatively light atom, it's fairly rare to find silicon in the universe. Carbon is 10 times more abundant in the universe than silicon. Although, on Earth, silicon is actually 1,000 times more abundant than carbon, making up a good chunk of our rocks here on Earth, like silicates. But that means you could argue that despite the fact that silicon is so abundant here on Earth, so much more abundant than carbon, life still developed here on Earth as carbon-based, which then you could say, okay, well then that means the probability of life being silicon-based is actually quite low. But maybe that's just on an Earth-like planet. Maybe when you combine that with a different solvent other than water, that's when you get silicon-based life thriving. It's just so hard to answer questions like that because you can't really do this in a lab, otherwise you're creating life as we don't know it. I mean, as astronomers, the universe is our lab. You've just got to find a planet first that you think has this different solvent and has silicon-based life forms. Hold that thought for a minute though while we talk about the last thing on our list, chirality, and whether you could have a mirror image of life here on Earth. Chirality, in my opinion, is one of the weirdest things in all of chemistry. Weirdest things in all of science, to be quite honest. So every molecule, which is a little combination of atoms, right, has a mirror version. So not rotated, but reflected. So like your hands, right? Your hands are chiral. Like there's no way that you can rotate your right hand and make it look exactly like your left hand does because they're mirror images of each other. The only way to make your left hand look like your right hand is to look at it in a mirror. It's the same with molecules, but instead of right and left-handed, they're referred to as like R and S pairs or D and L pairs. And if they are chiral, despite having the exact same chemical makeup, so the same atoms and the same bonds, they will behave completely differently. So for example, there's a molecule called carvone, and R-carvone is what gives spearmint its minty smell, but its exact mirror opposite, S-carvone, is what gives caraway seeds their like earthy, spicy smell. Even things like glucose, i.e. sugar, is chiral. D-glucose naturally occurs in nature, but L-glucose can only be made in the lab. And get this, it tastes exactly the same, but it cannot be used by life as an energy source because it can't get used in all of the biochemical reactions. Even things like proteins, amino acids, and DNA are chiral. So perhaps there is an Earth-like planet out there that at first glance looks to have life that it is very similar to Earth's, but in fact, it is actually a mirror opposite of life here on Earth using all of the different chiral molecules. But the big question is how we would find this life, but not as we know it. Or more importantly, how do we know that what we think we found would actually give us evidence of the existence of life? Because think about it. Even if we found the most Earth-like planet that's the same size and the same mass and it's orbiting, a sun-like star at around about the same distance that the Earth does from the sun, and say we study its atmosphere using the Hubble Space Telescope or the James Webb Space Telescope, and we look for which molecules are present in that atmosphere from the imprint that they leave on the starlight that passes through the atmosphere, and we find that there's all the signatures that we associate with life here on Earth, like water and carbon dioxide and methane and dimethyl sulphide. So much so that this planet was pretty much an identical copy of Earth, an Earth version 2.0. We would still not know for sure whether there was life on that planet. You could probably explain that planet's atmosphere through just chemistry and not biochemistry that needs life. But each of those models, one containing life just as we know it and one having no life at all, would have a probability in favour of it based on the evidence that we had collected. So sure, that planet would be the highest probability candidate for hosting life, but we'd still never know for sure unless we sent a spacecraft to that planet, which, given the light-year-long distances involved, we currently don't have the technology to do that. So if that's the case for life as we know it here on Earth, then you can probably see the problem when it comes to life as we don't know it. Because even if we found a planet with, say, high concentrations of liquid sulphuric acid, with some signatures of molecules that could indicate biochemistry was going on in that solvent of sulphuric acid, there could still be another model of the atmosphere that you could make that would only involve just normal boring chemistry and no biochemistry, no life. And that probability would be a lot less than any Earth-like Earth life planet we could also potentially find. This is why, when it comes to the search for life on other planets out there in the universe, we search for life as we know it here on Earth, and not life as we don't know it. But that could change if, and that is a big if we find life here in our own solar system, perhaps on Mars or on Venus or on the moons of, say, Jupiter or Saturn, which might be completely different to life as we know it here on Earth, a different solvent or different organics or different chirality. And that would be really exciting in of itself, but also because it could teach us so much more about what we should look for when we look for planets in other star systems out there in the universe. Essentially, what it would do is take something from that category of life as we don't know it and move it and put it under the big umbrella of life as we do know it. If it didn't look like life to take place within it, providing that pathway. Airplane has like looped back round. You got further away. How did you get closer again? Bloody airplane is back again. You would think that we live on the Heathrow flight path with how many airplanes I hear going over when I try and film. I literally just think it's people out on joy rides on sunny days. And I don't begrudge them that, but they're annoying. Or environmental differences where life might have adapted to like stronger or weaker gravity, for example. I'm just going to focus purely on the biochemistry, like the fundamental, excuse me, where did she jump up? We searched for life, we found it. What are you clicking on my mouse for? What are you looking at? I don't want your tail touched. Okay.